In past videos, I've talked about colligative properties of solutions, kind of how the concentration of a solution impacts the property of the solvent. So how much of the solute that I have is going to change the physical properties of the thing that it's dissolved into. But in ionic solutions, because of the dissociation between of the ions, so because ionic compounds split apart, and we've talked about this before in the Ionic theory of solutions. So Svante Arrhenius is one of the ones who said, well, ionic compounds don't actually stay as an ionic compound. They separate, they dissociate, they split apart into their component ions. And so when I'm thinking about colligative properties then, which are dependent on the concentration of the solution, it's not just dependent on the concentration of the ionic compound, because I actually have more ions in solution, which is a greater concentration. So it's dependent on the concentration of the ions, and we have to factor that in. So we not only have to factor in how many ions the compound can dissociate into, but we also have to account for how much it dissociates. Is it complete dissociation, 100% of it splits apart? Is it only a partial dissociation, so it's some sort of percentage of the whole? That all needs to be accounted for, and we can do that with what is called the Hoff Factor, which is a lowercase I for reasons that I don't understand. So for ionic solids, if I have 100% dissociation, then the Hoff factor, that I value, is equal to the number of ions. So if we take sodium chloride, which is a very soluble compound, then the Hoff factor is going to be 2, because I have a sodium ion and a chloride ion when this thing separates in its solution. And we're talking aqueous solutions here usually. If you have a solution that is, just nonmetals with other nonmetals, we're talking about molecular compounds and not ionic compounds, and then that's sort of a separate set of rules, right? Your Hoff factor is essentially just 1 if the thing doesn't dissociate. But for anything that can dissociate into its component pieces, if I have something like 6 molar sodium chloride, that means that I have 6 moles of my sodium ions and 6 moles of my chloride ions for every 1 liter of the solution. So it actually goes up by twice the amount, because each of those ions has this same kind of impact on the properties of that solvent. Now if I look at calcium nitrate, which is also quite soluble, it separates into calcium ions, and then I have 2 of these nitrate ions. So total, my Hoff factor is going to be 3, right? So it's really, for ionic compounds, if we assume 100% dissociation, then the Hoff factor, or the multiplying factor, is going to be equal to the number of the ions that are in that, or the number of formula units that are in that compound. So formula units can include things like polyatomics, which the polyatomic itself does not split apart. It is all one charged thing that is going to impact the concentration. Okay, so how does it impact the concentration? Well, it acts as a multiplier, because like I said, if I had 6 molar sodium chloride, then I really have 6 moles of each of those ions. So because my Hoff factor is 2, then it's going to be twice as concentrated when I'm thinking about how much stuff I have in my solution. So we have to factor this in for colligative properties, and I've kind of listed off the main ones. You'll find specific videos about each one. For freezing point depression, which is the increase of a solute which lowers the freezing point, then we just add it as a multiplier in there. Whatever the Hoff factor is, times the freezing point depression constant, times the molal concentration, will give me how much the freezing point is going to go down. For boiling point elevation, same thing. So we know the boiling point increases when I increase my solute concentration. The Hoff factor acts as a multiplier, so that times the boiling point elevation constant times the molal concentration gives me kind of how much my boiling point is going to go up from the solvent's normal boiling point. Then we have vapor pressure lowering, which is related to that boiling point elevation. So when the boiling point goes up, the vapor pressure goes down. By how much? This is Raoult's law, and it acts as a multiplier in front of that, where the partial pressure of the solvent, the pure solvent, times the mole fraction. Sorry, that's kind of a weird X. The mole fraction of whatever my solute is, then I'd have my multiplier there, my Hoff factor, and then osmotic pressure as well. So this kind of is derived from PV equals nRT. So pi here is equal to the molarity times R, which is their gas constant, times the absolute temperature. And again, my Hoff factor acts as a multiplier. Now, like I said before, if we have 100% dissociation, then that I is going to be a whole number, but it doesn't have to be a whole number. If I have only partial dissociation, then I might have something that's like a third, or maybe I have 2.5. It just kind of depends on how well these ionic compounds split apart. And depending on how much information you have about that, then you can factor that in. Oftentimes in a general chemistry context, they'll tell you to assume 100% dissociation. If it doesn't tell you to assume that, then you might have to calculate it. It might come out to be a non-round number, and that's okay. It just really depends on how soluble that ionic compound is, how much it splits apart in solution. And that's kind of the main takeaway from all of this. So kind of we add it as a multiplier. The Van Hoff factor can be determined based on the chemical formula, and that's more of an impact obviously with ionic compounds that readily dissociate in solution. If you have any questions on this, don't hesitate to reach out. Otherwise, I'll talk to you again soon.